All right. Sorry, I was doing a little bit piggyback and realized I forgot to let the graduate students know where they were supposed to go. So today is going to be pretty brief. I don't know if either of you guys know, but I think most of the others know. I am recovering from having the coronavirus. And so I have to carry around this stupid oxygen tank anywhere and constantly measure my blood oxygenation levels to make sure I'm not talking myself into brain damage. So today we're going to talk about what we're going to be doing in this class, kind of go over the syllabus, and then decide on a direction. And I'll explain what I mean by that as soon as I can figure out how to get this stupid projector to work. There are 4 undergraduate students and 4 grad students. Let's see what happens. Let's connect this. Okay. Now I need to, where do I go? Display. No, I don't want to Bing how to get to the display options. I want you to just show them to me. Two's computer. Let's see. And all right, it's terrifying seeing myself on a big screen like that. So let me find the syllabus. And then let me share it on Zoom so that everybody else can see a recording of it because nobody's showing it. Let's see, share screen. All right, so you guys are lucky in as much as there's only 2 here, so you get to make all the decisions for the class. I know that both of you guys know me because you've had me before, but I'm Dr. Hartman. All my office hours are done via Zoom this quarter. I'm trying to mitigate my interactions with other people to both protect them and me from getting it again, because being in the hospital for a week with this crap is pretty awful. In the event that the campus closes because of the coronavirus or another hurricane or tornado or whatever, we will continue the class using Moodle and Zoom. Let's see. Course objectives. At the end of this quarter, students should be familiar with design, simulation, testing, and manufacturing of analog CMOS integrated circuits. We're actually going to be doing specifically a multi-stage op-amp. That is the end goal of this class, is to design from the initial, it's called like a startup circuit that makes the astable multivibrator not astable anymore, all the way to a push-pull amplifier at the output stage. We're going to be going through the basic building blocks like current mirrors and simple CMOS-based amplifiers, so kind of similar to what you guys did in ELEN 335 and 336, but we're going to be working on chaining everything together to create a multi-stage op-amp, single supply, 0 to 5 volts input and output. The textbook and reading material. So usually in my classes, I try to avoid having to have a textbook, but Jake Baker's CMOS circuit design, layout, and simulation is literally the Bible of this material. It's used in both academia and industry. So at the very least, go illegally download the 3rd edition from somewhere on the internet, but I would highly encourage you to actually buy this textbook. One of the few times where I think buying the textbook is legitimately appropriate. For supplemental materials, and I'm not expecting you guys to buy these books by any stretch of the imagination. If we need to use them, I'll make a copy and give it to you. But we have Fundamentals of Microelectronics by Bazad Razavi and Design of Analog CMOS Integrated Circuits by the same one. 2 different books by the same guy on roughly the same topic. But they both kind of approach it in slightly different ways. All right, let's see. Disability disclosure, that's pretty much boilerplate. Class attendance is pretty much boilerplate. Academic misconduct, don't cheat. You guys that have had me before know how much I absolutely hate grading homework and how bad I am at returning it in a timely fashion. So to that end, homework in this class doesn't count for anything. And so what I mean by that is I'm going to give you assignments. I will happily look them over, but you're not required to turn them in. They're more or less a study guide over the material that we covered in that lecture that you would be expected to know for the exam. For the exams, there's going to be 2 take-home exams. The reason that I'm doing take-home exams is twofold. One, I had to miss the first 2 days of class because I was still under quarantine, and I wasn't sure that I'd be able to talk for even 20 minutes without running out of breath. And 2 is last year, the undergraduate students had one test and the graduate students had a different test. The test was only different by literally 1 single question. Grad students had to answer 1 extra question. And the undergrad students' average was, I think, a 95. And the grad students' average was a 50. So to not wind up failing most of the grad students their first quarter here at Tech, I'm giving everybody a take-home test so that you'll be able to use your book, notes, online reference materials, and all that kind of stuff to be able to thoroughly answer the questions and not completely screw over your academic career within the first couple of weeks of you being here. My intention is for the take-home exam to take a student roughly 3 to 4 hours to do total, but I'm going to give you a week to do, so that if you have other exams or other pressing matters, you can still not have to freak out about my stupid test. Let's see. There is an IC schematic and an IC layout project, and those are really what the focus of this class is about, is how to create those files and design our integrated circuit. So we're going to start working on that probably actually on Tuesday to some extent. So the weighting of the grading is 30% for each exams, and then 20% for the schematic and 20% for the layout. And as per usual, I do not curve. I don't think I'll need to change the syllabus, but if I do, I'll let you know. Emergency notification system stuff. And then here's all the boilerplate stuff that we're required to put on our syllabi now because of the pandemic. All right, so here's a list of the topics that we're going to be covering in this class. And I have not included a tentative course schedule because that's what we're going to talk about today. So we are going to be designing an op-amp, as I've stated before, building off of a lot of the topics that we learned in 335 and 336. And we're going to dive deeper into those and introduce new topics as well. We're going to be dealing with schematic capture and spice modeling. So we're going to be using LT spice a lot in this class to model the behavior of our op amps to make sure that it's operating the way that we intend it to, because it's very easy to accidentally flub something and completely eliminate all of the headroom of your amplifier, meaning that your amplifier can't actually amplify a signal. So we have to be like super critically careful about how we bias things using the minimum acceptable voltages and all that kind of stuff, how we generate those minimum acceptable voltages in order to allow our op amp to behave as an op amp, really. We're going to be doing, excuse me, designs for test and for manufacture. We are not going to be able to send off the stuff to Moses to get fabricated this year because the lead time is well over a year at this point due to the pandemic. So like anything that you created, if we sent it off, we wouldn't get anything back until probably 2023. So to me, that doesn't seem like a whole heck of a lot of a point. That being said, we're going to learn about a lot about the manufacturing process and how to make our designs comply to be able to be fabricated. We're going to learn a lot about the integrated circuit layout, including how to create the process mask layers, what each of them do, things like that. EDA design rule check and layout versus schematic. So this is where the two different paths meet. So we're going to be designing a schematic and we're going to be designing a layout, and we have to make sure that they represent literally the exact same thing, or all of our design rules and all that kind of stuff fail. We want to make sure that our schematic representation of the bits and pieces of our op amp matches our layout so that all of our simulations are an accurate predictor of how our circuit will behave. And then lastly, or not lastly, excuse me, we're going to be talking about parasitic extraction. And the reason we're going to be talking about this is pretty much everything that you can think of creates either a parasitic resistance or a parasitic capacitance in an integrated circuit. It's actually kind of baffling how hard it is to not create parasitics. And so we are going to be investigating the effects of those parasitic capacitances and resistances on the operation of our circuit, how to minimize their effects, how to minimize their existence and things like that. And then as time permits, we'll talk about more modern integrated circuit topics like FinFETs and multi-gate transistors and non-silicon processes. For example, at the Air Force Research Labs up at Wright-Patt in Ohio, they don't use silicon anymore for pretty much any of their sensors that they make. They use GaN or gallium nitride, and it's largely because of the temperature dependence on gallium nitride, or really the temperature stability. So we're going to talk about some of those type of topics as well, because we are rapidly moving away from simplistic silicon-based integrated circuit chips, because we've made things so small that the bulk silicon properties that we're used to are no longer really applicable as we go down beyond, I think, like 11 nanometer processes and stuff like that. So we're going to talk about where the future of integrated circuit design is going as we have time. All right, so excuse me. So that's a syllabus. So what I want to talk to you guys about today is how we're going to approach this, because there's really two discrete paths. One towards our schematic, where we have to understand very, very well how a MOSFET transistor operates and how we can use it to create resistances, capacitances, bias it to make diodes, all that kind of good stuff, the fundamental building blocks of creating a MOSFET circuit. The other path is how do we lay out all those things, and how do the different layers of the CMOS fabrication process interact with each other. And that's going to go a lot into how are we minimizing our parasitics, and things like that. And so they both kind of depend on each other. So we could approach this class from, we tackle the schematic side first, or we could approach this class from we tackle the layout side first. The layout way is maybe less math intensive and probably contains the most new information for you undergraduates, but it's the opposite relationship for the graduate students. Like, it probably contains less new information because of some of the classes that they're required to take. And then the schematic is more similar to what you guys did in 336. So it's going to be a lot of review, where for some of the graduate students who weren't here, it's going to be all new. So it really just depends on which series of topics you guys want to cover first. Like, if you, in the textbook, if you want to start at chapter 1 or start at chapter 9. So in your 437 class, you will be touching on some of the layout stuff, but largely what you're going to learn in that class is the processes behind the mask fabrication. So what I mean by that is you're going to learn about like photolithography and wet chemical etching and things like that. So you're going to learn about how the layers are processed to get the result that you want, but not necessarily what the layer is actually for in a CMOS integrated circuit, if that makes sense. Right. Yes. Okay. John, do you have any thoughts? No thoughts. All right. Grant, you're on Zoom there. Do you have anything to say?
No.
All right. So we have one vote for going with layout stuff first, and then 2 people abstaining, and the other 5 people didn't show up, so they don't get a vote. So we're going to go with the layout stuff first, which is exactly how I taught it last year. TJ taught it the opposite direction, schematic stuff first, and then the layout. All right, so goodness. So over the weekend, I'm going to throw some information online about where to download Electric VLSI, which is our layout tool. I think you guys probably, did you use it a little bit in 336? Okay, so we're going to be using Electric VLSI to handle our layouts, and we're also going to be using LT Spice, I think it's 14 at this point, to be doing all of our simulations, and excuse me, we're going to integrate those 2 software packages to be able to do our parasitic extraction, which you guys may have a little bit of experience already doing, depending on whether or not Prashana bothered to teach that part of 336. If not, not a big deal. All right, so I think that's enough out of me for today, because I'm starting to sweat from talking too much and I'm losing my voice. So I will see you guys on Tuesday morning, and we'll dive in to the material as much as we can. All right, thank you guys, and I'll catch you later.
So since you won't be able to send out, you won't be able to make the IC, so you won't have the lab.
No, I have the old ICs for the lab, so you guys can characterize those. Yeah, I have, I think, around 30 of them. So yeah, you're still going to be able to do the lab, and you're still going to be able to graduate. That is a no way I'm going to screw that up for you guys. Mr. Alam, I apologize for getting the link up and all that kind of stuff so late. Today we just kind of went over the syllabus and talked about the direction that the class is going to take. And I am kind of running out of breath and stuff, as I'm still waiting for my lungs to heal from having the coronavirus. So we've wrapped up for today, but I'll be posting this, everything that we talked about, the video on Moodle. And then we will start with our first real lecture and all that kind of jazz on Tuesday.
It's all right, sir. I'll go through all the documents you have uploaded on the Moodle. So it's all right. We'll join from the next Tuesday.
It's no problem that you were late. It's entirely my fault. I forgot to tell the graduate students where to go and all that kind of good stuff. So that's on me, not on you at all. So I apologize for that. I didn't think about it until I got here and saw only 2 students, and I was like, oh crap, I think I forgot to do something. So that's on me.
All right.
All right. Well, thank you very much, and I will see you on Tuesday.
Thank you, sir.